So you should be able to see. So I don't know how many of you have known your any peers in this class, but we are supposed to have a much bigger attendance than the current size. I don't know if you know any peers. No, you're just attending on your own. Yeah, but I'm not sure. But checking the record is much bigger than the size. I'm not sure because people saw the recording, so they wouldn't come. But I don't know if you prefer to have the recording or not. I'm still, yeah. Sorry.
It's because I'm recording this. Well,
Yeah, but still, I think in-person attendance is nice. Maybe people are not used to it after the pandemic, but I think it's nice because then you can get a chance to ask questions, right? I'm expecting this for our graduate students because I think most of, I would say everyone is a graduate student, either MS or PhD. But yeah, I don't know. So if you know your peers, maybe encourage them to come. But I will try to send an announcement to Bruno Learn because for the previous 2 Monday lectures, I know it's a special time and location. So I think it's understandable that people may not be able to make it, but this is the regular time, right? And we did have many students in the first lecture, and I didn't know why people stopped coming. Yeah. Anyway, so I hope you can ask more questions for those of you who are here. And let's continue our lectures. As I said, we have the previous recordings available, and I hope you can make use of that for better learning outcome of this class. So that's why during the class, I'll try to just, how to say it? I'll try to give you the highlights of the most important things in the lecture. So first of all, for those of you who didn't attend the Monday lecture in person, I want to say that we mostly talked about model diagnostics. In particular, in the setting of a linear model, these things, standardized residual, jackknife residual, are all trying to help you identify outlier observations. So say you have n observations, 1 to n, we want to identify the outlier observations so that their residuals are too large. That's it. And because we want to, in the calculation of the standardized residual, we need to have this variance, I will say standard deviation of the error term sigma involved. So just to start from the beginning, why do we want to standardize? The reason is that for different residuals, they don't have the same variance. They're not an error term, and their variance depends on the hat matrix, the HII. So because of that, we want to standardize it. But then the involvement of sigma requires an estimation of sigma itself. Then it comes to the question whether we want to include the observation I in our estimation of sigma, because the observation I, if it's an outlier, it would have a big effect on the estimation of sigma. That's why we have the jackknife residual, in which when we estimate the sigma, we exclude data point or observation I. And then we said that for the jackknife residual, there is this closed form formula for which you are allowed to just use the standardized residual, which is calculated by just fitting a linear model for once using all n observations, and convert that to this jackknife residual. So you don't have to actually do n linear regression, because otherwise for jackknife, it means that every time I exclude my observation I, use the n-1 points to fit a linear regression, and do so it requires n regressions. But using this formula, we just need to do 1 regression. Yeah. And the rule of thumb here, for the jackknife residual, this one, and the standardized residual, these are about deciding which observations are likely outliers. And this rule of thumb comes from the 1.96, the critical value for standard normal distribution. So we basically rounded 1.96 to number 2. Okay, and this is just a very interesting connection about this jackknife residual and this testing formulation. Basically, we can introduce another, I would say, dummy variable z which indicates whether the ith data point is an outlier or not. By introducing that, it becomes that, okay, if you want to test for data point I being an outlier, we are testing whether the coefficient of z, this gamma, is 0 or not. Okay, so that's another interpretation of the jackknife residual. So that's almost what we have last time. And then besides the outlier, we have two ways to look at the influence of observation on the beta. So outlier is just comparing yi and yi hat, which, let me try to change the direction here. Yi and yi hat, so that we hope yi, the observed response of I, and yi hat are close to each other. But if their difference is too big, we call it outlier. But for this, the leverage and Cook's distance are about checking the influence of a data point or observation I on the overall beta estimate on the fitted linear model. So leverage says that without seeing Y, without using Y, if you just use the design matrix itself, you will be able, let me make this brighter. Yeah, you will be able to decide whether a data point has a larger potential influence on the line or not. So this is from the last lecture. We're just saying that if we have just one predictor, the leverage is just depending on the distance between the predictor value to the center, to the mean of the predictor values. So if it's far away from the mean, then the data point is likely to have a large influence on the line, right? So you will change the line direction if it's here. But it's potential influence because you don't use Y yet. You are just using the hat matrix. The ith diagonal entry of the hat matrix define that as the leverage, as the potential influence. But if you want the actual influence, it's the Cook's distance. So in this case, you will compare the two beta estimates. One is beta hat, one is beta hat I. So beta hat I is the fitted beta estimate, the beta has estimate by excluding the ith observation from it. And then this is like in the form of the wall test statistic, because you have this quadratic matrix form. You have this variance hat. Basically, it's the estimated variance of the estimator beta hat. So just as I recall, the variance of beta hat is sigma square x transpose x inverse. And we plug in sigma square hat as the variance hat. And we take the inverse of that. So this is just to account for the variance covariance matrix of beta hat. And then we divide this by the number of predictors P. So essentially, here, the Cook's distance, this rule of thumb is depending on chi-square distribution. Basically, we have the numerator approximately following a chi-square distribution with P degrees of freedom. Then for such a chi-square distribution, the expectation is P. So that's why once we divide P, the expectation becomes 1. And that's why we compare this DI to the rough approximate expectation. That's just the rule of thumb. So Cook's distance evaluates the actual influence of a data point on the overall beta. So for all these things, standardized residual, jackknife residual, and leverage and Cook's distance, we are examining the influence of one observation I. And then our decision will be, do we want to exclude this observation from our data and do the model fitting again, or do we want to keep it? So, as I said in the last lecture, this is applied to the setting where your sample size is not that big, and therefore the influence of one particular observation is very important to consider. And I think this is still the case for some social science problems and also biomedical science problems where your sample size is not that big. Every data point is precious. Okay, so then we said that if you want to check the overall model fitting, this is it. So we want to plot this residual plot where you plot every residual against yi hat. So it's EI against yi hat. And you can replace this EI by SI for standardized residual, or TI, the jackknife residual. So a normal residual plot or a well-behaved residual plot should have the scatter of EI centered at 0, given each y-hat, and the scatter should be largely stable as you move along y-hat. That's what you want to see. But if you see something like this, there is a clear correlation between EI and y-hat. This usually indicates that the linear model is misspecified. By misspecification, it's a statistical language. We mean that the model doesn't fit well to your data. So then you need to modify your model and see whether you have a better model, right? Another thing is to check the normal distribution assumption. So we use the standardized residual, jackknife residual, assuming that they should be approximately standard normal distributed. So therefore, we expect to compare the distribution of these SIs or TIs against the standard normal and do the QQ plot. Expect to see a straight line. But if we don't see a straight line, last time we said that you should be able to do some diagnostics to see, okay, what does the QQ plot tell you? If it's a QQ plot like this, does it mean that the empirical distribution is more heavy-tailed or more light-tailed than standard normal distribution? So that's all about what we did in the last lecture. Today, we will talk about data transformation. So when the linear model seems to be misspecified, what can you do? If you want to use a linear model, then you want to transform your variables, right? Either transform your Y or transform your predictors. So the first idea is that we keep the linear structure on our predictors, but we transform our Y. So for this, Box-Cox transformation in 1964 is a very interesting way to transform the Y. So specifically, you introduce a new parameter called lambda. And then for lambda, you actually have it as a real value scalar. And then you consider for different lambda values, you transform the yi in different ways. So lambda equals 0 is the special case. We just set this to be log yi. So log y, you can imagine, it's nonlinear transformation, but it's monotone transformation, right? It only applies to yi being positive. Otherwise, log 0 is negative infinity, and we don't define log on negative values. So yi must be positive to apply this log yi transform. But what essentially does is that for the very large and positive yi, after you do the log transformation, they're not so large. So you're basically shrinking the large positive values to help you make the linear model more likely to fit. But besides lambda being 0, you also have other lambda values to do this. So basically, you put lambda in the power of y. So it's yi to the power lambda minus 1 divided by lambda. So you see, the fact that when you define yi parenthesis lambda, so this is defined as the Box-Cox transformation with parameter lambda, you have this derivative property. So once you do it, you would actually have the derivative just as yi to the power lambda minus 1. So basically, we're trying to use lambda to enable different sorts of nonlinear transformation. So hopefully, for some lambda, we can shrink large positive values to be not so extreme. But for some other lambda, you may make the differences between small values, small yi values, maybe the values close to 0, to make them more different from each other. So you're trying to use the nonlinear transformation to change the data, but keep the relative orders of y1 to yn. So the relative orders are still there, so because these are monotone transformation. So with this, then the linear model will use yi parenthesis lambda as the new response instead of yi. And as we're still using a linear model, the systematic structure, now here I want to clarify, now this mu I is defined as the mean of yi lambda. It's not the mean of yi. That's the key thing. So mu I, pay attention here, is the mean of yi lambda. So the systematic structure is still linear. It's that the mu I for the expectation of yi lambda is the linear function of your predictors. But the random structure is assuming that yi lambda follows a normal distribution with mean mu I instead of yi. So basically, the Box-Cox transformation intuition is that we try to do a nonlinear monotone transformation of our response so that the transformed new response satisfy a linear model. That's the intuition. Yeah, and you can see that this is something very generally applicable. Just to step a little back to look at the problem from a very high level, I think when we do modeling, statistical modeling, there are two general approaches. One is that we find a good model that best suits the data, best fits the data. But sometimes when your data is not like a Gaussian data or something easy to model with, coming up with such a model may not be easy. And second, once you come with such a model, the optimization, when you want to estimate the parameters using the MLE, it may be computational intensive, right? It may be a very challenging optimization problem. So the second approach is that I try to do some transformation on my data so that a standard model, like linear model, becomes applicable to the data. So it's a different approach. But for this approach, well, I would say it can be done, and it's a solvable problem. But then if it's a problem, if you want to present the solution to some scientists who generate data, you need to convince them why the transformation is reasonable, right? So that's why in this case, in the Box-Cox transformation, we still keep the relative rank order of y1 to ym, but we do the nonlinear transformation. So whether or not this is something justifiable, that is where the domain expertise part comes in. So that's why statistical modeling is always a combination of, I would say, mathematics, which is try to solve the problem, domain expertise, which is the question you want to solve, and also some philosophical thing, whether you prefer this approach or not. And sometimes there's no single best approach. So that's the subjective part of statistical modeling. Okay, so then after we have the random structure, systematic structure like this, we just do our regular likelihood writing, right? So basically, we still have our beta as the coefficient vector. We still have the sigma square as the error term variance, but we have this additional parameter lambda introduced for Box-Cox transformation. Because, you know, in this setting, we want to make it general enough. We are not trying to say we know what is a lambda. So lambda will also be given by maximum likelihood estimation. So therefore, when we write the likelihood as a product of the density function of individual observations, we keep lambda here. All right. But one thing we need to be very careful is that there is a change of variable thing. So by change of variable, this is a probabilistic result. Yeah.
Is it worse now to estimate 3 parameters as opposed to only 2? Because, you know,
It's not worse. Okay, when you say worse, it depends on what's the comparison. Compared to what, right? Because in this case, if you don't have additional knowledge about how to transform your Y, you might have from the domain expertise, right? Maybe you will say, okay, I know the nature of my data. So I know that the data is for sure not Gaussian. Then I know, okay, by doing the log transformation, the data is more Gaussian. Then in this case, you would directly use log yi as your response instead of doing this Box-Cox transformation. But this is for the case where you don't know how to transform your y. Then you have to estimate this lambda, right? And including this parameter is the right approach. Instead of just using some lambda you guess from the data and use it, because that's something we call double dipping. You are using the data, but you pretend that you don't use it. Then you are basically hiding that confirmation bias here. Yeah. So that's why here we keep the lambda, and the lambda itself will be estimated from data together with beta and sigma square. Yeah. Okay. Yeah. So this change of variable thing is about the density of y, and y is, sorry, there's density of x is g, density of y is f, and there is a functional relationship between x and y. So if we know x is y squared, then we can actually use this change of density formula to get the density of y. That's what we have. Okay, so you can go from the density of x to the density of y. And here, why do we need that? It's because we have the Gaussian that give us the density of yi lambda. But what we need here is the density of yi. And we don't have the density of yi. We only have the density of yi lambda. That's why we use the change of variable formula here. So that's here. So for the density of yi is the density of yi lambda times the absolute value of the derivative of dy lambda against dyi. And that's yi to the power lambda minus 1. And for yi lambda, the density g is from the normal distribution, from the random structure. And then we just write down the normal density. You see that theta sigma is here, yi lambda here, mu I is here, right? Just the normal density. The lambda is inside. And you need to keep this yi to the power lambda minus 1 to make this a correct density for yi. Okay, so one way to consider the change of variable is to consider this derivative part to be the volume change. So you will need to satisfy that the density is still a valid density, and the volume change may depend on the actual value of y. So that's why this dx dy is still a function of y. And once we have the likelihood, to maximize it, we typically use the log likelihood. The reason is that for the Gaussian case, the likelihood would involve an exponential function. But once we take the log, exponential function is gone. We're just maximizing the exponent, right? And that's equivalent. So then you see from this formula, we just have term by term. Because the likelihood will be a product of this term for I. So it's a product from, we'll do this, it's a product I from 1 to n, right? So once we take the derivative, the product becomes a summation of I from 1 to n. And the first term, it will appear n times in the product. So that's why we take the log, we get negative log 2 pi sigma and sigma squared, and the square root goes into this over 2, and n is from the power, n times. That's the first term. For the second term, the product will enter the exponential function as a summation. So we have the minus 1/2 from here, summation of this square term. So yi lambda minus xi transpose beta square over sigma square. Okay, these two are from the g yi lambda part. And for this part, we take the derivative, take the log, it became lambda minus 1 and the summation over log yi. That's why we have this log likelihood in this way. And the 3 parameters, sigma square, beta, lambda, they're all here. Okay. So compared to just the likelihood of a normal linear model without a Box-Cox transformation, we have this additional term here. This is from the Box-Cox transformation. And also in a normal linear model, yi should be here instead of yi lambda. Otherwise, it's the same. Okay. Do we have any questions or is it clear about this log likelihood formula? Can you easily see how it's derived? Okay. All right, then we will introduce this concept called profile likelihood. So profile likelihood is a way to represent our likelihood by allowing some parameters to depend on other parameters. So basically, we will simplify the likelihood, log likelihood, by having fewer parameters. And the way we achieve fewer parameters is by using some relationships among parameter estimates already. So basically, just to make it more clear, we would start by fixing lambda. So let's don't care about what value lambda is. Just think that there's a value, fixed value for lambda. Carry it over. So once you fix lambda, you see, when you want to optimize the likelihood in terms of beta and sigma square, then it's just the standard MLE for linear model, right? You only have beta and sigma square. So that's why here the beta hat would be X transpose X inverse X transpose Y lambda, because now the response is Y lambda, and you fix lambda, so lambda carries over, stays here. Sigma square hat is just the normal residual formula, Y lambda minus Y hat lambda. So this is the Y hat, the fitted value you get by fixing lambda. So pretending Y lambda is fixed, this residual transpose residual is just the RSS, right? Residual sum squares divided by degrees of freedom, n minus p. This is sigma square. And in both the beta hat and sigma square hat, lambda is assumed to be fixed. Okay. Then in profile likelihood, what we do is that we put the MLE for beta and sigma square given lambda back to the likelihood. Then you are only having lambda as the one parameter left, right? So because beta is replaced by beta hat lambda, you don't have beta anymore, you just have lambda. Sigma square is replaced by sigma square hat lambda. You only have lambda. So it's just like you're doing this kind of like gradient descent, right? You fix this dimension, you only optimize the other two dimensions and put it back. Then you have lambda as only parameter. Okay, so this is it. We call this profile likelihood LP. P stands for profile because it's still the same likelihood, but we replace beta sigma square by, I should put this back, beta hat lambda hat, beta hat lambda, sigma square hat lambda, and lambda. Then you have lambda as the only parameter. And then to find the lambda value, you optimize or maximize this profile likelihood. That's it. And once you have this lambda hat, you put it back to this formula, beta hat, lambda hat, you call this your final beta hat. And sigma square hat, lambda hat, you call this final sigma square hat. That's it. Okay. And I want to say that the maximization of the profile likelihood might not be easy. Yeah. So therefore, the optimization here is usually done via grid search. So basically you have 5 candidate lambda values carrying, so they carry different types of different nonlinear transformation on your Y. So you have -1, 0, 1/2, 1, and 2. So you may just choose among the 5 lambda values. If you are doing this way, then it becomes simple. For each lambda value, you input into the profile likelihood, get the profile likelihood value, and then choose the lambda value that give you the largest profile likelihood value. And that's your Box-Cox transformation. Okay, so any questions on this approach? Yeah, for example, if we go back to this thing, let me see. So if we go back to this problematic residual plot, it's possible that after you transform your Y, then you could have it more like the left one instead of the problematic right one. Yeah, then actually, after you do this, you should do the residual plot check again to see whether the transformation is reasonable. Okay, another way is to transform your X. You have P-1 predictors, right? If we have P including the intercept, then we have P-1 predictors. You want to transform the Jth predictor in a way. This is called feature engineering. So people have used this term more often nowadays. You want to engineer some powerful features for prediction. So it could be that you transform your xij. So I is the ith observation, j is the jth feature. It's possible that you transform it in a quadratic form, so it's monotone, but you actually, how to say, exaggerate your larger values. Or you could transform it in the square root type of thing. This is similar to log in the shape because you are shrinking your very large values. Or if you want to keep the sign of your feature, because the quadratic function would remove the sign, right? Because a negative xij and positive xij will become the same square value. You could keep the sign by adding the negative sign here. So then it's still monotone transformation, but you exaggerate large absolute values. Or you could actually, for the square root, you could actually add a negative sign to the negative values to make it become positive. Then you can do the square root. So these are the typical choices people can play with for transforming individual features. But I would say that sometimes you could add your transform feature into your model and let your model decide which one is more useful. So that's why nowadays, I would say in the past 20 years, people like using approaches like the lasso or elastic net to automatically select informative features instead of manual doing feature selection. So in that case, you can add the transform variables along with the original predictors. You can add, for example, xj square together with xj to your model to see how much improvement you can get from the model fitting. But one thing we should be careful is about the collinearity, because if it's monotone transformation, for example, if your xij square is like this, then it's very highly correlated with xij. Then this collinearity thing would not affect the prediction. So if we just want to get a yi hat, we don't need to worry about that. But if you want to get beta, the corresponding coefficient estimate for xj and xj square, then the collinearity will make the two estimates more random, more variable than they should be. So this is from the fact that, let me just write here. Yes, it's right here. From the fact that the variance covariance matrix beta hat depend on this x transpose x inverse. And x transpose x, if you consider every column j, xj to be centered and scaled to have standard deviation 1. This is the correlation matrix. And this p by p correlation matrix, if you take the inverse, its diagonal entries, the diagonal of the inverse matrix would be the variance of beta j hat, right? So that diagonal entry would be influenced by the off diagonal entries of xj transpose x. So that's why collinearity would affect the variance of beta j hat. And the best way for getting the small beta j hat variance is to have very orthogonal features. The more orthogonal your predictors of features are, the better you can estimate the effect, the beta hat j coefficient. That's something very important. So therefore, we need to be sure about what we want from doing linear regression. Is it for prediction? Is it for getting yi hats that are very close to yi's, or do we care about the beta? If we care about the beta, then having beta hats with small variances is very important. But I would say nowadays, given so many machine learning models, so many machine learning prediction models, probably when people use linear model, they care about beta, right? So it's more from this inference problem. You want to know the effect of the jth predictor on your y. So therefore, when you engineer new features, you should be careful about whether adding new features, your beta hat estimates are less accurate. So considering the variance is very, very critical, but it's not really used that much outside of statistics. So I think this is something statistics can play a very important role about the uncertainty of your parameter estimates. Okay, so that's it. And also just to clarify one more thing. Collinearity is often mentioned in linear model class, but I think some people are confused about whether it's like I said, it's an inference problem. Yes, it is, or a prediction problem. It is not. So if it's a prediction, collinearity is not that bad. You don't really need to worry too much if you just want to get the y hat to be close to y. But it's very important for interpreting how close beta hat is to beta. All right, that basically wraps up our linear model part. So we have spent quite 6, right? This is the lecture 6 on this linear model because it's the foundation. And once you understand it well, then we would just have very straightforward extension to variance. So our next topic is generalized linear model, short as GLM. So G stands for generalized. So what we generalize is in the random structure, yi, the ith observation for the response, is no longer Gaussian or normal distributed, but it still has its mean parameter of our interest. So we still call mu I as the mean of yi. So mu I is still the expectation of yi. There's no problem with that. And we still want to link mu I with our predictors, the p-1 predictors. But we do not force our mu I to be a direct linear function. We allow mu I to be transformed by a monotone function. And this is what we call link function that's invertible. So we need this link function g so that g mu I is a linear function of predictors. So one thing to be careful is that the linear part, the linear function of predictors, is taking values in the whole real line. So the range is from negative infinity to positive infinity, but mu i's range may not be. That's why we need this link function. And we call xi transpose beta as eta I, and we give a name as a linear predictor. So just in short, to summarize, G mu I equals eta I. So G function maps our or transforms our mu I to a linear predictor. Or we can say the linear predictor, which is the linear combination of our predictors, can be transformed to mu I via G inverse. And then mu I is the mean of the distribution of yi. So same as linear model, every yi has its own mu I, but the yi's are independent. So previously, yi's are independent normal distribution, normal random variables with different mu i's because the mu I depends on their xi. And they share the same sigma square, the error term variance. Okay, but now we want to move away from this normal assumption to be more general, to be other distributions, but we still focus on mu I. And mu I now we allow it to be transformed to be equal to the linear predictor. So systematic structure still has no randomness. It's only about the relationship between mu I and predictors using a linear model. Random structure is only about the randomness, how yi is distributed around mu I. Okay, so to motivate a generalized linear model, we will start from the most widely used generalized linear model, logistic regression for binary data. So I want to say that you might have learned logistic regression from a machine learning class or from the perspective of doing a binary classification. Yes, it is a method for that purpose, but we can also interpret the beta coefficient vector, which is the focus of this class. So logistic regression is very interesting because it's a model method that can be used for supervised learning perspective, for prediction, for predicting binary outcome. It's also something we can do inference for as a generalized linear model. So depending on you care about the prediction classification or whether you care about the beta hat meaning, and then that's just two different perspectives, but they can both be achieved using logistic regression. And still nowadays, I think for some classification tasks, especially if the problem is not very complicated, or if your features are very well engineered, I would just mention feature engineering. If you have strong features, logistic regression may be very powerful as a classifier. Just for your information, in the deep neural network for classification, the last layer is actually logistic regression, even though they call it softmax, right? Or they have this loss function way, but the loss function is actually equivalent to the MLE problem in logistic regression. So that's why you can consider the previous layers of your neural network to give you strong features. And then the last step would be the logistic regression for classification. All right, so we start from the setting that yi's, your response is binary. So there are many data like this. For example, if we look at voting data, every person has a binary vote, yes or no. And we have every person's characteristics. These can be used as predictors. For example, the person's, I'm just making it up, the person's education level, the person's income, how much will these change their voting preferences, right? This is the problem we're talking about. So for yi, of course, if it's binary, it doesn't make sense to assume it to be normally distributed. A normal random variable wouldn't be binary. What is the distribution for a binary random variable? Bernoulli. Bernoulli will naturally give you 0, 1 values. And Bernoulli has only one parameter, the mean parameter, we call it pi I. Pi I is the probability that yi takes value 1. Okay, it's the mean. So here, mu I is just, we use the mu I for general expectation of yi, and here it's just pi I. And its range is from 0 to 1. So therefore, if for such a mu I between 0 and 1, we cannot reasonably assume it to be xi transpose beta, because I transpose beta can take value from negative infinity to positive infinity. So the two ranges don't match. One is 0 to 1, one is negative infinity to positive infinity. What do we do? This is a function that's very useful. It's called a logit function. It maps the range 0 to 1 to negative infinity to positive infinity. So what it does is that for the yi, as it gets closer to 0, logit yi will go down to negative infinity. For yi, as it gets closer to 1, the logit pi I is going up to positive infinity. And it's symmetric at 0.5. So when pi I is 0.5, logit pi I is 0. So it's a function that satisfies the purpose so that we can have logit pi I match the range of xi transpose beta. All right, and what's logit? It's essentially defined as log of pi I over 1 minus pi. That's the definition of logit pi I. And how do we come up with this question? So I can show you the step-by-step consideration. First, pi I is from 0 to 1. Then we can easily see that pi I divided by 1 minus pi I is from 0 to infinity, to positive infinity. Because you can see as pi I gets close to 1, 1 minus pi will get close to 0. Then the ratio will go to positive infinity. But we still miss the negative part. What do? We know log can map 0 to negative infinity. And log positive infinity is still positive infinity. So by adding the log, we make the range go from negative infinity to positive infinity. And this is the logit function we end up getting. Okay, you can also use it in another way, the inverse of the logit function. Then it will map a negative infinity value to 0 and the positive infinity value to 1. So you can map a real line range to the 0, 1 interval range. And that's the inverse of the logit function. Okay, and I know in some fields like chemistry, people might use that inverse I think it's called logistic curve. I think that's a logistic curve, but this is logic. Yeah, I think that is something you want to study, the saturation effect of some chemical concentration. Like you increase the concentration, you have saturation raising towards some value, but you cannot go further up to positive infinity. Yeah, that's what happens in real life.
Also, like,
Yeah,
species.
yeah, exactly. Yeah, there's a saturation effect. So in this case, we have the logic pi I as our G mu I, because pi I is mu I, and we call this eta I, the linear predictor. All right. Then what we do is that for the systematic structure, what we have is you assume this is a linear predictor, and this is just a spelled out form of the linear predictor, right? This is just xi transpose beta. This is a vector inner product. We write it out element-wise. It's just xij times beta j sum over j. Therefore, beta j is interpreted in the logistic regression model as effect size of predictor j minus 1. Yeah, this is just like an indexing issue because we have the intercept. That's just it. But basically, it's just the effect size. And how do we interpret the effect size on pi I? Because pi I has a meaning. Pi I is the chance, in our example, pi I is the chance that voter I would vote yes, right? The probability voter I will vote yes. How do we check, how do we say the effect of predictor j minus 1, beta j on pi I? It's actually this form. So it's exponential of the linear predictor, or it's the exponential of the linear predictor on 1 plus exponential linear predictor. So basically, you would have pi I expressed in this way. And this way, you can easily see that because exponential is always positive. It goes from, how to say, it goes from 0 to positive infinity. When it divides 1 plus itself, it's always less than 1, right? But it's approaching 1 as it approaches positive infinity. Okay. Any questions about logistic regression? Yes.
Is there not like the consideration of like error?
Okay, very good question. Where is the error term? That's a question I used to ask in every class I taught this for. It's in the random structure. So you actually see in the normal linear model, once we write it as yi follows normal mu I sigma squared, we also didn't write out the error term. The error term's contribution is summarizing the normal distribution, right? Here, the randomness is in the Bernoulli. So let's say that you have two individuals, I and I prime. They share the same pi I. So maybe pi I equals pi I prime. But once you draw Bernoulli, two Bernoulli independently from the same pi I, you may get 1 for one person, 0 for another person. Especially when pi I is 0.5, that's where the largest randomness would happen, right? When pi I is 1, you will only get 1. When pi I is 0, you only get 0. But in the middle, that's where the randomness come from. So that's why in logistic regression, the randomness is assumed to be only in the Bernoulli. But the mean is specified by the predictor, totally. Yeah. So that's why sometimes people may say, oh, I don't think this Bernoulli alone can explain the variance I get, because you see, this will tell you exactly what's the variance. Variance of yi, we know the formula is pi I times 1 minus pi I. So that's why pi equals 0.5 give you the largest variance. Pi I being 1 or 0 give you 0 variance. So you have this form. But it's possible that your observed data will tell you, for people who have the same, how to say, predictors, maybe the variance of their yi's, if I take their zeros and ones, maybe they are bigger than this. It's possible. And that's why people call this over dispersion. And we will visit this topic later after we talk about logistic regression, Poisson regression, then we'll visit the over dispersion topic. So that's just like the random structure you assume here is not enough. Then how do you modify your model? Yeah, but it's a very good question. So when you have the Bernoulli, or later we'll have this as Poisson, you won't have an error term written out. The random structure, the distribution here explains the randomness. Yeah.
So I guess, is that contrast with the linear model, where like, it's assumed that the wires you draw us, the errors you draw. Distribution, that's what the error.
Yeah.
The error comes from.
So yeah, so let's just say, okay, just try to clarify. So there are two ways to write the same model. So one is, okay, for the linear model, let me just try to write it again. So yi equals xi transpose beta plus error. Yeah, epsilon I. This is the form you are familiar with, right? So we can assume the random structure. We can write down the random structure in two ways. One is that error IID normal. This is the random part. Then systematic part, structure. We will use this random structure, systematic structure throughout this class. It's mu I as xi transpose beta. That's one way to write it. Another way is that you directly write yi as independent normal mu I sigma square. So when you write when you use the right way, you don't need to write down sigma square. So you see, I can just have yi being normal mu I sigma square, mu I being xi transpose beta. So I don't need to spell out the error term. Yeah. Yeah, so now we are changing this to yi independent Bernoulli mu I for logistic regression. And later we will change it to yi independent Poisson mu I for count data. Yeah. Okay. Any further questions? Yeah, these are great questions. Especially, I saw a previous mistake. Sometimes even people who got PhD in statistics may make this mistake, honestly, because they may wrote this something like this. They will say, okay, yi. Okay, maybe they will say logistic. Let me just write it down. Logistic regression, I think it's common if you pay attention, is logit, let me just write it, logit pi I, I'm using the pi I notation, is xi transpose beta plus epsilon I. They may write the logistic regression this way. So in this case, it's not a systematic structure. It has randomness. And if you assume epsilon I or IID, normal, zero, mean, sigma squared, if this is what you wrote, then it's wrong in the sense that it's not logistic regression. Even though it's a model, it's another model, but we don't call it logistic regression. And it doesn't belong to the generalized linear model framework. Yeah. I hope this makes sense. And another thing to see here is that one is expectation of logit pi I is xi transpose beta. Right? You are assuming pi I is random. You're adding another layer to it. But what we have over here is just logit yi is xi transpose beta. We don't need to add expectation from out of the logit pi because pi I is not random. So therefore, the key thing is to think about randomness. What do we assume as random? So I like to say that whenever we use probability for our statistics. Whenever we say something is a random variable, we start making assumptions. So we should be very careful about that. But sometimes when you are trained in statistics, every textbook teach you random variable, you will get used to it, right? You take it for granted. You'll say, okay, something's a random variable. But when you do modeling, you need to think, should I call this a random variable or should it be considered fixed? Yeah. Yes. Yeah, that's something we will touch later. Yeah, there's a general theory for choosing the link function. Yeah, but right now, so far, how we talk about logistic regression, I would say this justification is from empirical. It's from like empirical observation. We try to match the range of this one, G mu I, the linear predictor eta I, we try to match the range to negative infinity to positive infinity. Yeah. That can do that. That's right. So that's why besides besides this logic function, we have something called probit function, which is, we'll talk about that later. You can do this. So this is the inverse of the CDF function of Gaussian, standard Gaussian. So I'll just say this is the CDF of normal 0, 1. So using this, we take the inverse because CDF function maps normal random variable from negative infinity to positive infinity to 0, 1, right? Then we take the inverse that would naturally satisfy this property. So that's why probit function, this is called probit, was used in the old days. It was in the literature, and it's just one of the many options. But later, the generalized linear model theory gave us a way to say, okay, some link functions can be called canonical link functions based on the GLM theory. And it happens that this logic function is the canonical link function. Yeah, so that's a nice way to justify it. Yeah. Maybe you now, I think it's a very great question because you see that if you don't use statistics, we can still do data analysis. We can analyze our data using whatever operations, right? But then what does statistics provide? I think it's some justification. Why this, not that? But if you don't know statistics, there are just too many options, right? And we know in some fields, people may not say, this is the best method, but I'm just using it. And it turns out to work well, and I report the results. It's probably fine, especially in scientific discoveries. Maybe you're still finding the scientific ground truth. But as we are doing this major, or I believe that statistics has evolved as a field in the past century because people still believe that when we don't know so much, then doing the data analysis in a more principled way with more justification is better than not. That is our belief. Yeah. Okay, so that's it. That's about the logistic regression for binary outcome. Then let's talk about logistic regression for group data. What do we mean by group data? So this is pretty common in social science data sets. That is, if you have yi's as binary, but some individuals, like in our individual voting example, some individuals, their predictor values may be identical. So if my predictor is just age, gender, education, if the education is like college, high school, graduate school, you will likely have multiple individuals share the same predictor values, right? They're all male high school students and whatever age range, like if it's 30 to 40, you may have these people share the same predictor values. Then you would not keep individual records, but you will group the data. So you would say, okay, for this group of people, they share the same predictor values, xi transpose, and there are ni of them. So here I becomes the ith group. Ith group with the same predictor values. So I just count in this group out of ni, how many people voted yes.
and that's my yi. So yi becomes a subset of ni that voted yes. So y is the sum of ones among the ni. So for each of the observations in ni, it's either 1 or 0, right? I take the sum, and that's my yi. So therefore, based on our previous discussion, if we assume the chance, the probability in Bernoulli only depends on predictor values, then people in the same group should have the same pi I. Same pi I for group I. And I have total of ni people. How many people voted yes becomes a binomial random variable. So binomial, total ni, probability pi I. So compared to the previous case, for individual level data, you may have each individual I have its own predictor values. So in that case, you don't do any grouping. Every individual is its own group. Then the group size is just 1. So that's why when binomial has the total size as 1, it degenerates to Bernoulli. So that's the fact. And we know that another important fact to know is that if you have independent Bernoulli random variables that share the same probability, their sum is binomial. And that's what we're using here. So for ith group, it has unique predictors, and n now becomes the total number of groups. So you still have I go from 1 to n. But you have n groups instead of n individuals. Each group has ni individuals. All right. And then as pi I is still 0 to 1 probability, we still transform it to logit to become real values, and it's xi transpose beta, and it's this. And we have the first predictor actually set to 1 just in the design matrix. This is the intercept. And pi I still has this exponential of linear predictor divided by 1 plus exponential linear predictor. All right, so if you want to know the jth predictor's effect on pi I, you could do the derivative. You want to just do derivative of pi I, the overall probability, against the jth predictor value in observation I. So pi I is group I should say group I's chance of being 1, and xij is the value group I has in predictor j. When you do the derivative, you actually get this beta j times pi j over 1 minus pi j. So the thing here is that it depends on pi I. So beta j alone doesn't tell you the effect of jth predictor on pi I. This is different from the linear model, because in the linear model, mu I is just xi transpose beta. If you take derivative against xij, you just get beta j. And beta j is the coefficient, is the only effect of predictor j on mu I. But once you move to logistic regression, pi I is itself involved in the effect. So it really depends on where pi I is. Again, you see that when pi I is close to 1 or 0, then the overall effect of beta j on pi I is close to 0. It's diminishing. This derivative is getting to 0. It's getting 0. But if the pi I is close to 0.5 in the middle, then the same beta j would have bigger effect on this observation. So be sure that this effect is specific to I. It's specific to group I. So therefore, for different I's, the effect is different. It depends on pi I. While in linear model, the effect on the right-hand side is no longer specific to I, to the ith observation or ith group. It's the same effect beta j for all observations. That's very different. So that's why for logistic regression model, when we talk about the effect of predictor j, it's specific to observation I. Is that clear? Okay. And I remember, Zhongtong, we had this conversation for the other day about this SHAP value, right? Yeah, I said that it's a feature importance value for deep learning, and it's defined as specific to I. It's a feature, in machine learning, people don't say observation I, they say instance I. It's instance specific feature importance value. Yeah, yeah. Okay. Then our next question, because we focus on inference in this class, right? Next question is, how do we estimate beta? And here, we will use the yi binary as the case, because we said the individual data where each observation is its own group is the more general case. So we use that to do the likelihood as likelihood calculation, for example, for the yi binary case. So again, we always use the random structure to give us the likelihood. Here, the parameters are what? Pi I for observation I. So we have pi 1 to pi n. And we can write the likelihood as the joint density of y1 to yn. So the independent assumption in the random structure is necessary. We have to use independence to factorize the joint density as a product of individual yi's densities. And actually, density here is just a general way to say it, because here yi are binary. So to be exact, we should say probability mass functions instead of density functions. Now here, but given the Bernoulli, the probability mass function is just pi I to the power yi times 1 minus pi I to the power 1 minus yi. Do we know why this is? It's because this generalizes the probability of Bernoulli, because when yi is 1, that probability is pi I. So this is exactly just pi I to the power 1 times 1 minus pi I to the power 0. So it's pi I. When yi is 0, the probability is 1 minus pi I. And this will also give us 1 minus pi I. So it's a general way to make yi being 1 and 0 possible using the same formula. And again, you see we have some power function in the likelihood. So therefore, it's much easier to work with log likelihood. Then we can get power down and we can change multiplication to summation. And that's what we have in the log likelihood. You see in the log likelihood, we change big L to small l. It's still log likelihood of pi, but the product becomes summation I from 1 to n, and pi yi gets down. We get yi times log pi I, 1 minus yi times log 1 minus pi I. And then we combine the terms by yi. Sorry, we have a yi times log pi I here, minus yi log 1 minus pi I here. So we combine it into this first term, and second term, log 1 minus pi I. So the combination here gets us logit, right? This is just logit pi I here. And then because of the systematic structure, recall that we have logit pi I as xi transpose beta. That's the systematic structure. Because of that, then we change log pi I over 1 over pi I as xi transpose beta. Beta comes in, right? And we want to find the beta value to maximize likelihood. Therefore, we will further change this pi I to beta. How do we do it? Recall this. Let's just scroll down a little bit. This is the relationship between pi I and beta. And right now we need 1 minus pi I here. So therefore you can see that 1 minus pi I right here is just 1 over 1 plus exponential xi transpose beta. This is just 1 minus pi I. And what we need here is plus 1 minus pi I. And we get minus log of the denominator, right? Because log of this whole thing is equal to minus log of the denominator. That's what we got here. Minus log 1 plus exponential to the power of x transpose beta. That's how we get here. So that's why now the log likelihood is just about beta and pi is gone. Because we link pi to beta using the systematic structure, using the link function. All right, then the task is MLE. How do we maximize this log likelihood of beta? This becomes an optimization problem. And the estimator, the maximizer is called beta hat. So that's the general introduction for logistic regression. So once we come back on next Monday, we will talk about the generalized linear model theory. So we will go back to the more general form, not specific to the logistic regression whose random structure is Bernoulli. We will generalize the random structure to be exponential family to see how in that general sense we derive the generalized linear model and also the optimization. So then logistic regression will just become a special case. Okay, so that's all for today. And then I'll see you next Monday.